Last class, we talked about buffers and some buffer situations and buffer range, the effective buffer range being approximately 1 pH unit above or below the pKa of the weak acid or weak base. We also have buffer capacity, which is not a particularly well-defined term necessarily. It's the amount of acid or base that you can add without causing a large change in pH. So what buffers do is they minimize large pH changes. A large change in pH probably indicates the buffer has been exhausted or depleted or broken, meaning we're missing either our weak acid or our conjugate base, or we're missing our weak base or the conjugate acid. We can increase our buffer capacity by increasing the amount of buffer components that we have. That'll let us add more acid or base into our buffer without it being exhausted on either of those ends. We can also increase our buffer capacity in some circumstances by increasing the relative concentrations. Equal amounts is optimal in many circumstances. That's like our best all-around buffer is going to be equal concentrations of acid and base. If we know that our buffer is going to primarily neutralize added acid or base, we can bump up the base or acid component of our buffer. And that will increase our ability to buffer out that acid or base. So for buffering lots of acid, have excess base. And the opposite would be true if we are buffering lots of base, we would want excess acid. And that's kind of all that we talk about buffer capacity. So the two things we can do, increase the absolute concentrations, more buffer component means more buffer capacity. We can also have closer to equal amounts if we want a good all-around buffer. And one conceptual question about it, a 1 liter buffer solution is 0.10 molar in hydrofluoric acid and 0.050 molar in sodium fluoride. Which action destroys the buffer? Is it adding this amount of HCl, adding the same amount of sodium hydroxide, adding the same amount of sodium fluoride, or none of the above? Our buffer contains 0.10 moles HF, just doing the molarity times the 1 liter, and 0.050 moles of sodium fluoride. Getting rid of either of those two components makes it no longer a buffer. So the sodium fluoride, that's our base. The HF is our acid. They're both weak. We can get rid of this base by adding in the same amount of acid. So if we add 0.050 moles of HCl, hydrochloric acid, then that will deplete the sodium fluoride. That will all turn back into hydrofluoric acid. So that should destroy the buffer. If we added the same amount of sodium hydroxide, that would use up about half of our amount of hydrofluoric acid. So that's not going to do anything. If we add that 0.05 moles of sodium fluoride, that's just going to make our buffer even stronger. Questions? Great. All right, some review of titration. We've been doing titrations in lab. You did titrations in 3A. If you took it, you did titrations in 1A. So we'll just review it somewhat quickly. When we're doing an acid-base titration, we're taking a solution of known concentration. We're reacting that with a solution of unknown concentration. One of those needs to be acid, the other needs to be base. And then we can monitor those either with a pH meter, like the vernier set that we're using, or an indicator, a colored dye that changes with pH. That's what we did in 3A and 1A. When we get to the equivalence point, the number of moles of acid is stoichiometrically equal to the number of moles of base. And that means that we have a neutral pH, usually. And that's our titration endpoint, our equivalence point. So the things that are equal at our equivalence point is our acid and our base. It's not always going to be neutral pH. We'll see some instances where it's not. And then we can calculate the concentration of the unknown since we know the volume of our known concentration solution. We'll see examples of that. So one that you've probably seen many times before is doing a titration like this. So we've got our sodium hydroxide solution loaded up in our burette. We have an acid in our Erlenmeyer flask. We add in sodium hydroxide to our Erlenmeyer flask, and initially it's a clear solution. We also have an indicator in our solution. As we get closer and closer to the equivalence point, we're using up our acid that's in our flask. We're making water, and so the pH of this solution is rising. The closer that we get to the equivalence point, the longer we'll get this pink color sticking around if we're using a phenolphthalein indicator like pictured here. And eventually we'll get to the equivalence point where we've exhausted all of our acid in solution. And the base turns the phenolphthalein, the indicator, fuchsia. Phenolphthalein isn't the only indicator that we have. There's actually a lot of indicators. That one's just really convenient for doing strong acids or strong bases. Both. If we're doing a plot of our pH, we can generate something that looks like this graph on the right. So we've got the volume of sodium hydroxide that we added, basically time that we've added solution at a steady drip rate, and our pH plotted on the y-axis. We would have to use a pH probe to generate a plot like this, like we've been doing in lab. So initially we started with 1 molar strong acid, or 0.1 molar, sorry, of strong acid, and we're adding in our sodium hydroxide, slowly neutralizing our acid, and then it spikes here. And at this middle point, this point of inflection, when our slope changes, that is our equivalence point. And with our verniers, we were looking at sometimes a first order plot, which shows our slope over time, and you'd look for the peak of that slope. If you do a second order or a second derivative plot, then that's when you would see your inflection point as a 0, or where your graph goes up towards infinity and then comes up from negative infinity. The asymptote of those two would be your equivalence point. So there's a couple of ways that we were looking at that. And when we're near that equivalence point, our pH is going to change very quickly because we're rapidly changing the balance from being acid-dominated to being hydroxide-dominated. It'll change very quickly, and since we're exhausting all of our acid, it quickly goes into base-dominated, and so the pH is much higher. And the shape depends on a bunch of factors. We'll talk about some of those, but acid and base strength play a role here. So this is a strong acid with a strong base. We'll also sometimes find it helpful to express concentrations or amounts in milli units, so using this milli prefix. We'll often measure in milliliters, and concentrations will be in moles per liter. That'll result in us changing between milliliters and liters, and then back to milliliters. So it might be helpful instead to use millimoles. So one way that we can do that is by changing our molarity to millimoles per milliliter. Alternatively, the milli prefix can just carry through the calculation. I don't think I've shown this for this class, but I think I've shown it to my 1A last semester. Or you can just convert from milliliters to liters and then convert back to milliliters later. It doesn't really matter. This is just if you want to save a little bit of time, you feel comfortable doing that, you're welcome to do it that way. All right, let's look at titration. We want to calculate for the titration of 25 milliliters of 0.1 molar hydrochloric acid. That's going to be titrated with 0.1 molar sodium hydroxide. We want to calculate the volume of sodium hydroxide to reach our equivalence point. And we're given an acid-base neutralization reaction for those two. So to start, we are given a volume and a molarity. Both of those look like they're a single unit. Secretly, molarity is moles per liter. I think it's very helpful to just be able to mentally switch between capital M and moles per liter. We can swap those out. They're interchangeable, and that makes molarity look an awful lot like a conversion factor, which is how I like to use it. So 25 milliliters is what I would start with here, since it's just a single unit. So 25 milliliters, and that's for the HCl. So we want to find how much sodium hydroxide do we need to add. So looking for volume sodium hydroxide. So this 25 milliliters of HCl, we need to get rid of milliliters and go to moles so that we can use the stoichiometry from our balanced equation. So we're going to multiply by 0.100 moles per liter the concentration of our HCl. So our liters cancels our liters. Notice that the milli didn't get canceled out. I'm doing that strategically here. So now the units that we'll have is millimoles of HCl. We can then do the stoichiometry step. We have a 1-to-1 ratio between HCl and sodium hydroxide. So our numbers aren't going to change. HCl goes on the bottom, sodium hydroxide goes on the top. This is an important step to remember anytime we're doing a diprotic or triprotic acid or base that releases multiple equivalents. Okay, so our HCl's cancel. We now have millimoles of sodium hydroxide, and we're given the concentration of the sodium hydroxide, and so we can implement that now. We're going to divide by that concentration, since that'll put the moles on the bottom and the liters on top. And then our moles cancel. The milliliters, the liters, the sodium hydroxide all come through, and we'll end up with 25.0 milliliters sodium hydroxide. You can also do it with what we saw before on the previous slide. This might be a little easier for keeping track of that milli, doing millimoles over milliliters. Just write that in real quick in case that's helpful for anyone. So our milliliters cancel. We would have millimoles. We'd have millimoles later as well. And our HCl's cancel out at some point. So then we have milliliters over on the back end. If you do it this first way, you just have to be very careful that you don't forget about the milli that we had at the start, because that'll throw you off. Either way, you'll get the same 25.0 milliliters of sodium hydroxide. So second way is a little easier for remembering that milli, otherwise they're the same. All right, let's say that we're doing this titration. We want to check a couple of steps along the way. There's an opportunity to do a tremendous amount of math here. We're going to skip some of the math. Hopefully I remember to skip some of the math. But we're going to just look at the titration kind of stepwise as we're going through things. So initially, our pH in the Erlenmeyer flask, the thing that we've got down below, is our strong acid. We've got 25 milliliters of a 0.100 molar HCl solution. So our concentration of HCl, 0.100 molar. pH is equal to the negative log of the concentration of H plus or hydronium. Since HCl is a strong acid, it's going to be equal to 0.100 molar. So our pH is negative log of 0.100, which is 1. And that's what we see represented by this first point, the 0 point on our graph. When we add in a little bit of sodium hydroxide, we can also calculate the pH at those further steps. So we would start by using a stoichiometry table. So this is like when we were doing those two steps, and one of them's not a nice table and the other's nice table. This is the not a nice table part. So we're starting off with our initial number of moles. So for the H3O plus, it's 25.0 milliliters times 0.100 millimoles per milliliter. So that's how we end up with 2.50 moles. And we've added 5 milliliters of our sodium hydroxide. So our initial amount of hydroxide, the amount that we're adding in, is 5 milliliters times 0.100 millimoles per milliliter. So the milliliters cancel. We know that hydroxide and hydronium react to form water, and so we're going to use up all of one of these two. In this case, our hydroxide is the smaller amount, so we're going to get rid of all of our hydroxide, and we're going to get rid of a stoichiometric proportion of H3O plus, just the same number of millimoles. That will mean that all of our hydroxide gets used up, and we've got some remaining H3O plus. In millimoles. Now we've added also a little bit of volume. We've added 5 milliliters of solution, and so our total volume is now 30 milliliters. After adding the 5 milliliters of sodium hydroxide. So we have to account for what's our number of moles or millimoles of our acid or our base, and also what our new volume is, because that's going to also affect our solution concentration. And so we get that our H3O plus concentration is 0.0667 molar, and then we can negative log that to get our pH value, and it doesn't go up very much. It's not written out here, so I'll go ahead and do that. It's 1.18 or thereabouts. So our pH hasn't gone up very much. We still have a lot of our hydronium in solution. And we can calculate this for any amount of volume of sodium hydroxide that we want to. Obviously, that's a little bit of a waste of time. It would just be doing the same calculation over and over again, and I don't think it's especially challenging or especially entertaining, and so we're going to skip all of that. And so the calculations have been done and tabulated here for you for those 10, 15, and 20 milliliter steps. And all these solutions are still H3O plus dominated, meaning that's still what we have in the majority for all three of those points. If we add 5 more milliliters, then that gets us to 25 milliliters of sodium hydroxide. We had calculated that as our equivalence point earlier. So we can do an initial change and end table for this. Our H3O plus OH minus is going to go to H2O. This is how the table had been set up for us previously. Our 25 milliliters of 0.100 millimoles per milliliter solution We saw that calculation earlier. That's our amount of H3O plus that we started in the flask. So it's 2.50 millimoles. We've also added the same volume of the same concentration of sodium hydroxide, so the calculation is going to be the same. That means that we've got 2.50 millimoles of hydroxide. Since these two amounts are the same and they're used up in a 1-to-1 ratio, that means that our change is negative 2.50 millimoles. And so at the end, we've got no more of our added H3O plus or hydroxide. That means that all we have left is water. And if we're at 25 degrees Celsius, then we know that pure water has a pH of 7. So that's why our pH is 7 there at our equivalence point. If we go 5 more milliliters, now 30 milliliters times 0.1 we've added 3 millimoles of hydroxide. We still have the same initial moles of H3O plus. And so we have excess hydroxide. We use up all of our H3O plus. We're past the equivalence point. We've got 0.5 millimoles left. So 0.50 millimoles of hydroxide. And our total volume, so calculating the hydroxide concentration, our total volume is 25 milliliters. That's our volume of HCl that we started with, plus the 30 milliliters of sodium hydroxide. So 0.5 divided by 55, that gives us a concentration of hydroxide of 0.0090, and that 90 looks like it repeats, molar. To convert that into pH, the way that I would prefer to do it is find the pOH. So negative log of that concentration. So our pOH is 2.04. 14 minus that number, 14 minus pOH equals pH. And our pH here is going to be 11.96, thereabouts, or 12.0 for 3 sig figs. And we can see on our graph our 30 milliliters data point is just a little bit below 12 for pH. We can do the rest of the steps adding in even more hydroxide. So our pH increases slightly as hydroxide concentration increases. And again, lots of opportunity to do not very entertaining and not very insightful math, so we're just going to skip it. And that would wrap out our titration. So overall, these are kind of the important parts of the graph. We had our initial pH that we calculated. We had our H3O excess. As our pH is slowly starting to rise, we're depleting our H3O plus. And then around the equivalence point, our pH changes very rapidly as we're shifting from an H3O excess to a hydroxide excess. At our equivalence point for the strong acid and strong base, we have a pH of 7. After our equivalence point, once we've already used up all of our strong acid, our base concentration is dominant, and it'll slowly rise, sort of approaching the concentration of our hydroxide solution. Questions about any of those steps? So that's kind of the less interesting of the titration situations that we can get ourselves into. There's another one that's equally uninteresting, in my opinion. That's titration of a strong base with a strong acid. So this is starting with base in the flask instead of acid. So we're starting with a high pH, adding acid in, and our pH curve looks about the same. And since it's a strong base and a strong acid, our equivalence point is pH 7. So just flip the thing, and it's that. All right, let's see if we can do those calculations. I'll give you a little time to work on this. A 50 milliliter sample of 0.200 molar sodium hydroxide is titrated with 0.200 molar nitric acid. Calculate the pH after adding in 60 milliliters of nitric acid. We'll come back in a couple minutes. All right, coming back after a brief pause. We've got a sample of a concentration of sodium hydroxide. We also have an amount of nitric acid and a concentration for the nitric acid, and we're trying to calculate our pH. So we want to know how much acid have we added, how much base have we added, and then we'll see how much we have left after we do the reaction. So 50.0 milliliters of sodium hydroxide multiplied by our concentration, expressing that in millimoles per milliliter, just so that our milli is easy to keep track of, should get 10.0 millimoles sodium hydroxide. Sodium hydroxide is a strong base, and so that's going to be 10.0 millimoles of hydroxide. We can do the same calculation for our nitric acid, 60.0 milliliters of HNO3 times the same concentration, milliliters cancel, and we get 12.0 millimoles of nitric acid. Since it's a strong acid, that's going to mean that we've got 12.0 millimoles of H3O plus or H plus, however you want to write it. So that's what we'll put in for our initial amounts in our little, not a nice table, but looks like a nice table. So H3O plus sodium hydroxide, hydroxide. So for our H3O plus, we've got 12 millimoles. For our hydroxide, we've got 10 millimoles. Those react in a 1-to-1 ratio. So they're going to lose, we're going to use up 10 millimoles of both. So we're depleting our hydroxide. So we've got 0 hydroxide left, and we'll have 2 millimoles left of our H3O plus. So we can calculate our concentration of H3O plus. It's going to be the millimoles that we have left over divided by our total volume. And our total volume is the combination of the 50 milliliters of sodium hydroxide plus our 60 milliliters of nitric acid that we added. So 2 divided by 110, our concentration is, that in red, our concentration is 0.018, and that 18 looks like it's repeating. And it's molar, since we will end up with millimoles over milliliters. The millis cancel, we're left with moles per liter. And then our last little step, pH equals negative log of our concentration. So negative log of 0.01818181818, etc. 1.74-ish for our pH. Questions about any of the steps there?
How do you know which one to subtract when you're doing the ice table thing?
So when we're doing the change, we're subtracting the smaller of the two.
Okay.
These, the acid and the base are going to react until there's nothing left of one of them. One of them will get used up. If we're at our equivalence point, they'll both get used up. So it's just whichever is the smaller of the two. We're finding which one is in excess, basically. There's probably another way to do it without doing a table, but I think that the table way is a fine way of doing it. So yeah, just subtracting the smaller of the two. All right, we've got this diagram that I don't think is particularly helpful out of the book, but that's okay. We've got an amount of strong acid in our flask here. Which mark on our burette, based on where these little molecule representations are, or ion representations are, which mark on the burette indicates the amount of base required to reach the equivalence point? Let's assume that A is the smallest amount, meaning that we would dispense everything below A. B is slightly more, meaning we dispense everything below B, and so on.
D.
D as in D?
Yeah.
So the way that we would solve this, we count up the number of H pluses that we have. We've got 3 up top here, 4 down here. We've got 7 H plus. In order to reach our equivalence point, we need 7 hydroxide. So 1, 2, 3, 4, 5, 6, 7. That's our 7th hydroxide, so we'll need to add in 7 hydroxides. The correct answer is D, D. Now here's the more interesting titrations. If we're titrating a weak acid with a strong base, let's look at the equivalence point for this reaction. So we've got sodium hydroxide, and I think this is formic acid. So 25 milliliters of formic acid at that concentration. We're adding in sodium hydroxide. To reach our equivalence point, starting with 25.0 milliliters HCHO2, we can convert that using our concentration. So 0.100 millimoles per milliliter. That's our concentration of our, I think, formic acid. So we now have the number of millimoles, and then we can do a stoichiometry step. Let's do that in red. So our ratio is 1 to 1. Our number is not going to change, but our chemical will. HCHO2 on the bottom, sodium hydroxide up top. And then we can convert to milliliters for our last step. So divide by 0.100 millimoles. That puts milliliters on top. And we'll get a volume of 25.0 milliliters, because the 0.1s cancel each other out. So we need to add 25 milliliters of sodium hydroxide to get to our equivalence point. We can do this with different concentrations as well. The volume depends on the amount in moles of acid, not really on the strength. So changing the volume or changing the concentrations will end up with slightly different numbers. The calculation ends up being basically the same though. Now, something that's different about doing a titration with a weak acid instead of a strong acid is that we've neutralized all of the added H+. However, notice that we've got sodium formate. This CHO2 is the conjugate base. And it's the conjugate base of a weak acid, meaning that it is itself a weak base. So that's what makes these calculations more interesting, or these titrations a little more interesting. We can look at our initial pH. It's going to be a little bit different than doing it with a strong acid. So before adding any base, just looking at the 25 milliliters and the 0.100 molar HCHO2, our concentration, doing an ice table this time to figure out how much H3O plus and CHO2 minus we have. So because we have a Ka value, we need an ice table. So we've got our initial concentration. It does have to be in concentration. We've got our change. Since we don't have any of our conjugate base or this formate anion, we're going to be moving left to right. We got some Le Chatelier's principle stuff going on. So we get negative x plus x plus x. And so we end up with this for our Ka expression after we substitute in. Our Ka value is 10 to the minus 4, so we're probably good to use, we're at least close for our x's small approximation. So 0.100 times our Ka value equals x squared to get rid of the squared, square root both sides. So x is equal to x is equal to 0.00424 ... which is the same as our H3O plus concentration. So pH is 2.37 or thereabouts. Just as a reminder, we can check our x is small approximation. So our x value over our initial concentration. So 0.0042 ... over 0.100 times 100%, we get 4.24%. That's less than 5%, so our x is small approximation works here. All right, when we add a little bit of sodium hydroxide, we use our not an ice table. So we added a little bit of hydroxide that's going to use up or turn our weak acid into conjugate base. So we now have conjugate base to consider in this table. So we're adding 0.500 millimoles of that, and our moles after looks like this. So 2 millimoles, 0.500 millimoles. Note that this table is in moles. It's not an ice table. It's more of a stoichiometry table. We want to calculate our pH after adding in those 5 milliliters of sodium hydroxide. Fortunately for us, we've got an equation for that. We have a Ka value for our weak acid, and you may remember pH equals pKa plus log concentration of the conjugate base over concentration of the acid. We don't have our concentration of the conjugate base or of the acid since we added in 5 milliliters, so we'll need to find our new volume. It's 30 milliliters. So let's calculate our concentrations of our CHO2 minus and our HCHO2. It's going to be 0.500 millimoles over 30 milliliters. And our concentration of our weak acid is 2 millimoles over 30 milliliters. Let's look at what happens if we don't evaluate these, so don't plug these into our calculator, and we just plug them in for concentration of A minus and concentration of HA in the minuscule amount of room that I left myself. I'm going to actually scooch these over looks like an eyebrow. Oh no. 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 Okay. We'll just erase it and rewrite. No. Gosh dang it. We're having a good time. All right. We've moved the hat of our 5. So 1.8 times 10 to the minus 4 plus log, and the A minus is 0.500 over 30. The HA is 2.00, also over 30. So this 30, the one on top, would flip down to the denominator. The 30 in the bottom would flip up to the numerator. So those cancel each other out. We don't actually have to, since they're in the same solution, we don't have to worry about the volumes. It shouldn't make a difference. So that's potentially a nice little hack. So 1.8 e negative 4 plus log of 0.5 divided by 2. That's not right. What did I do? Oh, I see what I did. I put in Ka instead of pKa. So, great, 3.7. Or thereabouts. So I forgot to convert the Ka to pKa. That's why I ended up getting a negative number initially. Questions about that? There is, of course, more not particularly fun, not particularly interesting maths that we can do here. The one bit that is interesting is our half equivalence point. So that's this 12.5 milliliters bit, where we have equal amounts of acid and base. Equal acid and conjugate base. So our pH is equal to our pKa. And that might be nice, for example, if we know that we're using a weak acid, but we don't have a pKa value or a Ka value for it. This would be one way that we could determine that experimentally, perhaps. A situation that we're unlikely to run into. It might also, if we know the Ka and the pKa, be a nice check to see how we're doing with our titration. And then at our equivalence point, we've added 25 milliliters of sodium hydroxide. The buffer has been depleted. Since we have no more weak acid. And we just have our conjugate base acting as a weak base. And since it's a weak base, our equivalence point is no longer neutral. Our equivalence point is slightly basic. I think we have a calculation for calculating that pH on the next slide here. Oh, look at that. I even left in my scribbles from going through it last night. So our pH at the equivalence point, we've got our millimoles of our conjugate base at equivalence, so that 2.50 millimoles. Our volumes, our initial volume of the weak acid and the volume of base that we added. So we calculate our concentration of CHO2 minus. So that goes into our ice table. We're going to be producing some of our weak acid and hydroxide. So it's the negative X plus X plus X that we expect to see. And now that we've flipped our equation, right, this is a weak base. So we need the Kb. And that's why I've written down here in red, Kb is going to be the HCHO2 concentration times the hydroxide concentration over our conjugate base or weak base concentration. Ka times Kb at 25 degrees Celsius equals 1 times 10 to the minus 14. So our Kb should be 1 times 10 to the minus 14 over 1.8 times 10 to the minus 4. Or 5.5 repeating times 10 to the minus 11. We can definitely use our X's small approximation here because it's 10 to the minus 11, and that's how I simplified this down to X squared over 0.0500. So continuing the calculation to get our X by itself, the square root of our Kb times 0.05, X is 1.6 repeating times 10 to the minus 6. And since that's X, that's our hydroxide concentration, we can calculate our POH, which is 5.778, and some other stuff. 14 minus our POH gives us our pH. And finally, we arrive at a pH of 8.22. So a lot of little steps, kind of annoying, lots of things to remember, but I don't think it's overall that difficult. It's not crushingly difficult, at least. Any questions about doing that?
You got the 2.5 millimoles from the equivalence?
Yeah, so 2.50 millimoles on this previous table. We added 2.5 millimoles of hydroxide. We initially had 2.5 millimoles of our formic acid. Those get completely used up and in the process form 2.50 millimoles of our formate. And again, for our ice tables, these need to be in units of molarity. If we just use moles, we might end up getting the wrong answer. Okay, we'll stop there for today.